So welcome to Recognition 2. We have two talks before the award session. The first is going to be given by Ramon on Landmark in Enhanced Heuristics for goal recognition and incomplete domain models.
So my name is Ramon, and this work was developed in collaboration with André Pereira and Felipe Meneguzzi. And this work is basically about goal recognition in incomplete domain models. So what is the problem we want to solve here? So what we want to solve here is recognizing goals in complete domain models, and these incomplete domain models can possibly be incorrect. And because most approaches in goal and plan recognition assume that the domain model is complete and correct, and most approaches relax the need to deal with incomplete domain information. And in this work, we drop this assumption, and we deal with incomplete domain models. So, and how do we develop our approach to goal recognition? So in this work, we use no planners to perform the goal recognition task. And instead, we use new definitions of landmarks using these new definitions, we develop recognition heuristics. And to formalize incomplete domain models, we use incomplete strips with annotations to specify the incomplete part of the domain model as possible preconditions and possible effects in the action descriptions. So what is the main motivation of this work? So the first one is that we are moving forward to more realistic settings because, as I said before, most approaches assume that the domain model is complete and correct. And the other one is the lack of domain knowledge, because even for a domain expert, sometimes is very hard and complicated to define a domain model in a complete and correct way. So that's our main motivation. So now, very briefly, I'm going to show you what is incomplete strips and the concept of landmarks. So incomplete strips is very similar to the original strips, but here we have possible preconditions and possible effects in the action descriptions. That's the main difference between incomplete strips and the original strips. And we also have an incomplete strips planning problem. And here the only difference is that we have an incomplete set of actions. And we also have an initial state and a goal state and a set of facts. And so here we have an example of an incomplete strips operator. So here we have an action to move in a navigation domain. So here we have a possible precondition, which is that the from location must not be dirty before the agent moving. And as a possible effect, we have that after moving, the location to will be dirty. That's basically how we define incomplete strips operators in this work. So, and landmarks, you may know that landmarks are facts or actions that cannot be avoided to achieve a goal from an initial state. So, and landmarks can be necessary conditions actually. So, and we use this to build our heuristics in this work. And as I said before, we use no planners for the goal recognition process. We use actually new definitions of landmarks for incomplete domain models. So given the background, now I'm going to present to you the problem overview of this work and the problem formulation, and also how we extract landmarks in complete domain models and how we use this new definitions of landmarks to build our heuristics. So in this work, we assume that the goal recognizer has an incomplete domain model to perform the goal recognition tasks, while the observed agent is acting in planning an environment using a complete model. And it's important to emphasize that in this work, we do not change or improve the incomplete domain model. So we use the incomplete domain model the way it is. So that's the assumption we do in this work. And here we have this image to illustrate the problem overview. So we have the recognizer, and in pink we have the incomplete domain model. And the observed agent is using a complete model for planning his actions in this environment. And as the observations, we can have partial observations, we can have full observations, and we can also have noisy observations in this kind of environment. So, and the problem formulation is based on the work of Ramirez and Gaffner, but here we have an incomplete domain model, and we also have an initial state. So, and we also have a set of candidate goals, a set of goals that the agent possibly wants to achieve. And in this set, we have a correct hidden goal. And we also have a sequence of observations. In this case, we have actions as observations, as most goal recognition approach. So this is basically the problem formulation in this work, how we define the problem of goal recognition in incomplete domain models. So, as I said before, in this work we use no planars. So, and we use the concept of landmarks. So, and we had to adapt define new types of landmarks to extract landmarks in complete domain models. So to do so, we adapt the work of Hoffman et al. To extract landmarks in complete domain models. And instead of using the original relaxed planning graph, here we use an optimistic relaxed planning graph. So this is a new type of relaxed planning graph for incomplete domains. And the extraction process is exactly the same proposed by Hoffman. So the only modification we do, the only adaptation is the use of the optimistic relaxed planning graph. So, and this optimistic relaxed planning graph assumes the most optimistic conditions. So we ignore all possible preconditions and all possible delete effects of all actions. And we use all possible add effects of all actions. So that these are the optimistic conditions we use to build this optimistic relaxed planning graph. And similar to the original one, we use all known preconditions and add effects, and we ignore all possible delete effects. So here we have an example of an optimistic relaxed planning graph. So here we have the set of preconditions in green, and the dashed edges in pink, we have the possible add effects, and in orange, we have the add effects. So you can see that we can have more information using this optimistic relaxed planning graph, and therefore we can extract more landmarks using this, this new relaxed planning graph in incomplete domain models. And using this optimistic relaxed planning graph, we can we define new types of landmarks. So we have definite landmarks, landmarks that are real landmarks, that they are extracted from the complete part of the domain model. And we also have possible landmarks, landmarks that are extracted from the incomplete part of the domain model. So landmarks that we don't know for sure that they are landmarks, so they are extracted from the incomplete part. So here we have an example of a definite landmark. So consider that F0 is a landmark, and here we want to extract landmarks before F0. So we select the achievers of F0, in this case is A2, and then we select the preconditions of A2, in this case is F2. So why F2 is a definite landmark in this example? Because F2 was extracted from the complete part of the domain model, more specifically using a known add effect. So that's why F2 is a definite landmark in this example. And how do we extract possible landmarks? So consider that F2 in this case is a landmark. And again, we want to extract the landmarks before F2. And then we select the achievers of F2, in this case A1. And then the preconditions of A1, in this case F0 and F1. And why these are possible landmarks? Because they were extracted from the incomplete part of the domain model from a possible add effect of an achiever. So, and besides definite landmarks and possible landmarks, we also introduce another type of landmark, which are called overlooked landmarks. And these overlooked landmarks are landmarks that they were not extracted by approximate landmark extraction algorithms, because you may know that most algorithms to extract landmarks extract just a subset of landmarks. They do not extract all landmarks, and some landmarks are missing during the extraction. And we use this concept of overlooked landmarks to obtain more information from the observations. So consider that we have a fact F in the observations, and this fact is not a definite landmark or a possible landmark. So how do we check if this fact is a new landmark, is a landmark that was not extracted before? So we build an optimistic relaxed planning graph, removing all actions that achieve this fact. And then we test the solvability of the problem. If the problem is unsolvable, then this fact is an overlooked landmark. So, and we perform this verification on the fly during the Go recognition process. So now that we define the new types of landmarks, now I'm going to show you the heuristics we developed based on this new definition. So the first one is called Go Completion Heuristics. And this one uses and combine the new types of landmarks. So, and this heuristic is basically the ratio between achieved landmarks and the total number of landmarks for a goal. That's basically how this heuristic works. And here we have an example. Consider that we have a goal G, and this goal G has 8 landmarks in total. And as the number of achieved landmarks, we have 4. So, and computing the score, we have 0.5 as the score for this goal. So that's basically how we compute the heuristic estimation using this heuristic. And for the second heuristic, and we introduce a new concept, the concept of landmark uniqueness value, which is how unique a landmark is among all landmarks for all goals, because most goals share common landmarks. And here we want to verify how unique a landmark is among other landmarks. So here we have an example of uniqueness value. So consider these 3 goals, G1, G2, and G3. And the uniqueness value for the landmark A is 0.33 because it's common for all goals. And you can see that for B is 0.5 because it's common for G1 and G2. And C is just 1 because just G1 has this landmark, and for D is 1 as well because just G3 has this landmark. That's basically how we compute the landmark uniqueness value. So when we use this landmark uniqueness value to compute, similar to the other one, the achieved landmarks and the total number of landmarks, but here we use this concept. And the process is basically, the goal recognition process using landmarks is basically extracting landmarks for every goal from the initial state, and then compute the achieved landmarks, and then use the heuristic estimation to verify the score, and the goal with the highest score is the intended one. That's the goal recognition process. So regarding the experiments and evaluation, we use 15 domains to evaluate this approach. So we have navigation domains, logistic-based domains, and other domains. And in this work, we modified the complete domain model of the other data set by using an incomplete domain model with annotated possible preconditions and possible effects in this. And we varied the incompleteness of this domain from 20 to 80%. So we have 4 levels of domain completeness. And we also vary the percentage of observability as most approach to goal recognition. So we vary from 10 to 100%. So, and we evaluate this approach against a baseline, which is a heuristic for goal recognition that also uses landmarks. But here, we just use the concept of definite landmarks, because here we want to show that the new types of landmarks has a real impact in the goal recognition process. So we did an ablation study by combining the types of landmarks to see which one has a real impact in the goal recognition process. And you can see in detail in our paper the combination and the result. And the one that has better results was the combination of definite landmarks, possible landmarks, and overlooked landmarks. And here we can see that we surpass the heuristic surpass the baseline against the whole data set. So we have better results than the previous heuristic using just definite landmarks. And regarding the recognition time, you can see that it's very fast. Consider the extraction, not of the definite landmarks and possible landmarks, but also consider the overlooked landmarks. So the average in the data set over all problems is around 4 seconds. It's very fast. And to conclude, here we presented novel heuristics for goal recognition in complete domain models. We also developed an algorithm to extract landmarks in complete domain models. This algorithm can also be used for planning, not only for goal recognition. And the limitations of this work is dealing with low observability when you have just few observations and 80% of domain completeness. So sometimes you have no information to perform the goal recognition problem. That's the main limitation of this work. And as future work, we intend to deal with other type of domains. So perhaps using approximate transition functions and other constraints in this setting. And that's all. Thank you.
We have time for questions.
Okay.
Let's repeat the question.
Missing altogether some effects, not even among the possible effects. How would that come up?
Yeah, because we assume the optimistic condition, even if all effects are possible, we assume that all possible add effects will occur in the relaxed planning graph, so we still have information to extract landmarks.
But you are assuming the completeness with respect to the possible effects.
Yes. No, actually, we can add incorrect possible effects.
Yes. But still,
Yes.
if something happens, it is among the possible.
Yes. Correct.
Any other? Yes. I think you need the mic for the recording.
You said that you also can deal with noisy observations. I haven't seen that. Right, noisy means that you make a wrong observation.
Yes, that's
so
right.
How did that show up there?
Oh, actually, it can be, for example, an observation that it's not related to the environment. For example, consider a navigation domain, and then you see an agent pick up in some object. In this case, it's an action that it's not in the environment, or it's not allowed in that state, so it can be a noise in that case, for example. So we deal with that. So in our evaluation, we also evaluate our approach, not only dealing with missing observation, but also with noise observations, and also the domain completeness. So there's several levels of. Okay.
Any other? One last question? I have a short one.
Okay.
Well, it's continuation of a question that was here before, but basically you can support models where you don't have this closed world assumption where you have this set of possibilities, right? That would just be the subset of the landmarks that you mentioned as definite landmarks. You could just use them.
Yeah, actually the baseline, use just the definite landmarks,
right,
extracted from the complete part of the domain model. And we show here that the new types of landmarks has a real impact in the recognition process.
But you can't always assume that you have access to such information.
Yes.
So it's an added value to exist.
Yes, it is.
Okay, thank you. So thank you. Let's thank the speaker. Our next speaker is Jean, which will be talking about error-tolerant anytime approach for plan recognition using particle filtering.
It's already on.
You can use mine.
Oh, well, it's okay? Yeah. So I have the sound now. So yes, I will present my work with my colleague Mathieu Grahl and my PhD supervisor Éric Beaudry about error-tolerant in-time approach for plan cognition using a particle filter. So first, a bit of motivation. So this is the robot we're currently working on, which is Vigil. And Vigil is an assistive robot for elderly people for their daily living activities. But in order to assist these people, the robot needs to understand what they're doing. The problem of understanding what the person is doing and what the person intends to do in the future is basically plan recognition. In order to perform this plan recognition, we first need to choose a way to model the behavior of a person, both the goal and the action, and we choose to use the definition of partially ordered context-free grammar from Gabe and Goldman. So this definition represents plans as a set of goals, sub-goals, and action. It's HTN without the precognition and effects. This is the example I will use through the presentation. Usually, there's two ways of solving this kind of problem. You have the top-down approach, which consists in developing all possible explanation from your model and use a Bayesian, from the observation, use a Bayesian algorithm in order to find what is the most probable goal and what will be the most probable action in the future. The other approach is to use a bottom-up approach. So the bottom-up approach is exactly the opposite. You start from the action and you generate what is possible and you apply your Bayesian model only at the end. For example, if I have the action get kettle, if I have the, no, it's okay. So if I have the action get kettle, the only possible explanation is that I'm boiling water, which is the only possible explanation for that is I'm making some tea. So this is the exact opposite. Usually, bottom approaches are preferred because you only generate valid hypotheses, when with the top-down approach, you generate every possible hypothesis. Either way, there's two huge limitations for this kind of model. The first one is it's at least in p-odd and semi-decibel in the general context. And the second problem is that it's very sensible to noisy observations. Because these approaches are based on generating and filtering hypotheses, if you take into account noisy information, you have an hypothesis space too large, and usually the problem becomes intraceable. So these two limitations make the use of this kind of model for real-life application nearly impossible. There was a lot of work about how to make the system quicker and more reliable, either with offline algorithm or online algorithm. Most of them can handle the missing observation noise, which means if you don't see something, the system can continue to infer what can be the most probable goals. But nearly none of them can deal with mislabeled information or with extraneous actions. So the question here is how to adapt, how to find an algorithm that can deal with both the noisy observation and can provide reliable information as quick as possible. So first, a bit of definitions. So formally speaking, a plain library with formalism is a tuple with a set of actions, which are the terminal symbol, a set of non-terminal symbol, which is both the actions, both the goals and the sub-goals, and a set of calls, which is a subset of the non-terminal actions, of the non-terminal symbols. There's also a set of production rules, which are a set either of the non-terminal symbols and the symbols with a partial order. So like I said, with that, you can describe a hierarchical task network without the precognition and effect, like we have right there. With this example, you have 2 goals, 3 non-terminal symbols, 7 actions, and 3 production rules. You also need to have an accurate plan recognition system. You need to have a decision model. So the decision model is, it represents how a person has preferences over either a production rule or goals. So for us, it's just a priority distribution over the production rules. With our example, we create an artificial decision model with a person that would prefer to make hot chocolate than tea, and with 1/3 versus 2/3. Finally, we need something to describe the noise. So we introduce the noise function. So here the noise function is also a priority distribution of the set of action over itself, plus the empty symbol at the power p. So why adding the empty symbol and the power p? Well, because with this simple addition, we can represent with only one function all the three type of noisy observations. So the four behavior we can have, if you have the action A and you observe A, it's a correct observation. If you have the action A, you doesn't observe anything, it's a missing observation. A and you observe B is a mislabeled observation. And if instead of A, you see a set of actions of the length of P, it's the extraneous actions. So we introduced also the extend plan library model, which is basically the three combined. So you have the plan library, which represents how the world works. You have the decision model, which represents how the observant acts and thinks. And you have the noise function, which represents how the observant sees. So now we have a model. How can we solve it? How can we have plan recognition quickly and with the capability to tolerate some errors? Well, we propose to use particle filters. So what are particle filters? Let's say you have a Markov process X, and you have an observation function over this Markov process. A good way to have an estimation of what are the hidden states of your Markov process is to run as many simulations as possible, to filter them with what you observe in the real life, and just to count for every possible states what are the number of particles that have these particular states versus the total number of particles. So just a sampling algorithm mixed with a genetic algorithm. Algorithmically speaking, it's a four-step algorithm with initialization states, where you create a population with a size that you can determine before the algorithm. Then you have a transition function. So for each of element of your population, for each of our particles, you apply the transition, you simulate the transition of your model, and after that, you filter. So you observe the world, you see every particles that have a state that correspond to the observation you have. Everything that is not correct, you can delete it, and everything that is correct, you can keep it. After, you just have to regenerate your population by randomly choosing from your surviving particles. At any time, you can have what are the probabilities just by counting the number of particles with different aspects. So it's quite easy. The question now is, how can we use this model on the model we have for plan recognition? So what we propose to use is to use plan trees as particles. So this is the representation of the plan I've introduced earlier. The idea is that we will create, with a similar method of the top-down approach, we'll create some plan trees. And the hidden state will be the goals and the sub-goals. And what will be the observation function will be the action itself. So as an idea, if I create a particles, I randomly choose from T-making or Choco-making. If I choose T-making particles. And I will non-deterministically choose how the system will evolve. Here, for example, I can do as a first action to get some T. So it will be my state at T plus 1. At T plus 2, I can have another action, which could be, for example, getting T kettles. So here I have, on the right, I have what is hidden and what I want to find by just counting the particles. And on the left, I have what we call the ENO, expected next observation. So basically, it's what we think if the person do this particular plan, what the person will do next. And this is what we'll use to filter our particles. So with a more developed example, if I created with my model 30 particles, I will have around 10 particles of Choco-making, of T-making, 20 particles of Choco-making. I apply a transition for each one of them. I can range them depending on what will be the next expected observation. Then I will observe, and I see, for example, that the person is getting the mug. So I can delete every other particles, regenerate my initial population, and I can go so on, recreating, applying a new transition, filtering, etc., etc. The question is, now I have a particle filter approach for the plan recognition part. How can I add the noise to this part? Well, what we propose to do is to add the noise during the NO generation part. The idea is we applied the first transition, which is basically just choosing what is the next possible action. And at this particular moment, we add a mutation, which we use the noise function we had earlier. We apply it on the action, and we generate a new action, which can be the same as the beginning. And we can range the particle depending on this new possible observation. That way, we can keep the deterministic filtering we have earlier. So For example, here, if I have if I have the action tea kettle with an ambiguity, I don't know if he's getting the tea kettle or if he's filling it with water. Well, I will create several particles. Some of them will mutate. For example, one of the upper will mutate. And when I make my observation, if I have a noisy observation, for example, I observe fill water, but the correct action was get tea kettle, well, some particles with the good hidden state will survive. So we made some experiments about that. So we used the 15232 domain from Miski and al., which is basically an automatically generated HTN with 5 goals and 8 of 3, a branching factor of 2 UD for 3, 100 base action, and a partial redundancy of 33%. So the results, we divided the result into first, without noise. So we want to see if it's an accurate way of recognize plan. So we set a particle filter with several number of particles, so 50 to 500. And we see that at 500 particles, the accuracy is over 99.5%. Even with less particle, 250, we still have an accuracy over 90%. So it's pretty good results. Also, we of course test the speed of our algorithm, and for 10 observations, for a full plan, the algorithm can have the answer in less than 0.08 seconds, which is really, really fast. As a comparison, other algorithm, which, disclaimer, are offline, our is online, do this recognition in between 5 and 10 seconds. Concerning the noise, we test with 3 different number of particles, one with 250, one with 500, and one with 5,000. And we can see that the noise have a linear impact on the recognition. So if you have a 10% of noise, the accuracy of your algorithm will go to 100% with 500 particles to 80%. 20% noise, 80% accuracy, 30% noise, 70% of accuracy. 2 interesting facts is that when you double the numbers of particles in your particle filter, you don't improve the recognition. There's no improvement in augmenting the number of particles. The second interesting fact is that we test with several disposition of noise. So we tested with 20% of only missing observation, 20% of only mislabeled observation, 20% on only extraneous observation, and 20% with a mix of all. And what we can see is that within a narrow margin, all of them are around 80% of accuracy for 20% of noises. So as a conclusion, we propose a new online approach of CFG-based plan recognition, which is really quick without sacrificing the expressivity, and we can handle the noise quite efficiently without sacrificing the speed. One of our main work right now in our future work is about temporal constraint, because for plan recognition with this kind of model, usually temporal constraint is the easy way. The problem is that with a particle filter, we can't apply the same techniques. We have to find something new. Thank you. Have you got any questions?
Some very good talk. My question is, so it doesn't seem to me that this is that difficult to use a flat model like PDDL or something like that instead of the trees. Have you considered using classical planning domain rather than a tree-based one?
Yes, we have we didn't use PDDL domain only because we have one particular problem for the robots. We have a particular domain for the robots, and PDDL wasn't adapted for this one. But virtually, you could use the particle filter on other things. That's what we have.
Or on MDP maybe.
Of MDP. Well, it would probably work with PDDL, and it would probably work with MDPs too.
It's very good to add noise and errors in plan recognition.
Thank you.
However, if you implement this on the robot that you mentioned earlier,
yeah,
then you will not observe action. You will observe only their effects. Your sensors do not see action. They see only effects. It has always, I've always been surprised that plan recognition on the basis of action is not what you have in robotics. So how would you deal with that?
So it's a bit off topic about the articles, but the idea is that on the robots, on our particular problem, for daily living activities, you can use what we call object affordance. The idea is that your day-to-day activities can be determined by what your hand is in contact with. So basically, for the activity recognition part, so the lower part, all we do is recognize where's the hand, where's are the object, and if there are contact between the hand and the object, the system told to the plan recognition one that there's an activity, this is the activity.
But in that case, you deal with the noise and errors and the sensing errors at this level.
Yes. In fact, we deal with the errors on the two levels. First, on the activity recognition part, with some filters before giving it to the plan recognition part. So yeah, we filter errors both on the activity recognition and the plan recognition. Obviously, we can't do it only on the plan recognition part. We have to do the two. Yeah, of course. Of course.
Any other question? I have a short one.
Yes.
You talked about noise. It's also related to the previous question. You said that there was noise in the model, but when you defined the model, you said that the noise was in the observer's sensing. But when you generated the population, you actually you used probabilities to generate different behaviors.
Yes.
And can you say something about that? I was expecting populations to be generated according to the actor's model, but then the probabilities would come from how, from the noise in the sensor model.
Yes.
So I was a
No,
bit confused about that.
it's the both of them. That's why we have a double transition system. The first transition corresponds here, what I presented here. The first transition corresponds of the model, what I described earlier. The second transition is just adding the noise to the system. So it's just to like I show with the extended planar libraries, it's just to narrow the gap between what the observee do and what the observers see. The idea of using the particle filter is you are always on the point of view of the observant. You are not never on all the states of the observee are hidden. Each particle could be one of the situation, and the expected next observation is not only what the person will do, which is hidden. It's also what the person what the robot will see if the person is doing these particular actions. So it's cumulative.
Thank you. Thank you. One more question?
So my impression is that particle filters are extremely effective in low-dimensional spaces, but that they don't scale very well.
We add this impression too, and what we discover is that in general settings, it's rare that you have a problem with a really large space for what kind of utilization. Yes, if you imagine a full random HTN with several thousand of goals, we will need several hundreds of thousands of particles. But generally, when a person is doing a goal, you can filter to a few hypotheses before going to the plan recognition. For example, if someone is in the kitchen, you know that the number of the plans that depend on going to the bathroom are probably false. So you can narrow the number of goals for real-life application. But yes, you're right.
Okay, thank you. Let's thank the speaker. And